I'm Anil Kumar, and in this video we will discuss and try to understand what are rational functions. Basically, rational functions are ratios of two polynomials. So let us say if we have a polynomial n of x and we have another polynomial d of x, in that case the quotient of these polynomials, that is to say n of x over d of x, will be termed as a rational function, right? So here is an expression which I have written for rational function. R of x is my rational function, which is quotient of two polynomials. N of x I am using for numerator, d for denominator. Remember, denominator cannot be 0, so that causes restrictions. So all the rational functions are expected to have restrictions, and they may or may not have. So we'll explore that aspect also. So that means there could be restrictions on the domain of rational functions, correct? Now let us start with some examples. The simplest form of a rational function, I will say, is 1 over x. Now 1 is treated as a polynomial, x is treated as a polynomial, so 1 over x is a rational function. We could have a rational function like 2a over b. So that is also a rational function. A polynomial divided by another polynomial where a and b are variables, correct? So we could have 2x squared y over 4xy, correct? So that will also be a rational function. So in these rational functions, always, since you cannot divide by 0, we will have a restrictions which should be written, clearly written I should say, as x is not equal to 0. In this case the restriction is that b is not equal to 0. In this case the restriction is 4 cannot be 0, it is a constant, so x and y are not equal to 0. So those are the kind of restrictions which will always be there on a rational function. Now all the reciprocal functions, for example, if I have a function x minus 1, well, even if I write x minus 1, it will be treated as a rational function. Why? I could write this as x minus 1 over 1. So this is also a rational function, right? So remember, even if I am writing a function without any denominator, we can always assume the denominator to be 1. So it becomes a rational function, correct? So all polynomial functions can be treated as rational functions in general, right? So that is what we can say. Now, what are not rational functions? Let me write down in red. What are not rational functions? As I'm saying, rational functions are ratios of polynomials or quotients of polynomials. So if I write something like square root x over x plus 1. Now here square root x is not a polynomial, therefore it is not a rational function. If I write 1 over sine x, this is not a rational function since sine x is not a representative of a polynomial. Similarly, e to the power of x over 1 plus 2, x is not a rational function since e to the power of x is not a polynomial, right? So these are examples of not polynomials. We could have radical roots like 2 over 3, right, plus x to the power of minus 1. That is not a rational function. So wherever you will see that we have any other function than polynomials involved, then those combinations are not rational functions, right? So that is kind of important to understand. Now in general, now we will consider a few restrictions, how to write restrictions for a rational function. So normally if I write, for example, x plus 2 over x minus 3, in that case, if I substitute x equals to 3 in the denominator, I get 0. So that is a restriction on this particular function. So the method to find restriction is to equate denominator to 0. And then denominator should not be 0, leads to restriction. So in this case, we'll say x minus 3 cannot be equal to 0, so x is not equal to 3. So that is how you write restriction for this particular function. If I have a quadratic function or a complicated function, for example, if I have x plus 2 over, instead of x minus 3x, let us say we have 2x plus 6x squared. In that case, we can actually factor the denominator, right? So we could write this function as x plus 2 divided by, we could take 2x common, and we get x plus 3x. 2x common, so we get 1 plus 3x, correct? Now in this case, 2x cannot be 0. That means one restriction is that x is not equal to 0. The other restriction is that x is not equal to minus 1 over 3. So by factoring and then equating the denominator to 0, we can find restrictions on the rational functions. So that is another part of rational functions which we are going to explore further in details. Now let us also have a quick look on the graph of rational functions. So as I said, 1 over x is the simplest of all. So normally if I have 1 over x, and if I want to sketch this parent function, it is reciprocal of a line. So the function can be graphed as shown here. So this is the graph for 1 over x. Now since x is not equal to 0, we represent it by, in this case, a vertical asymptote, right? Like that is better. So we'll say x is not equal to 0. So there will be a vertical asymptote. Now this vertical asymptote represents that as the value of x approaches 0, from positive side 1 over x becomes positively high. As the value of x approaches 0, from the negative side, that means 0.1, 0.001 from the negative side, then it becomes negatively high value. So that arrow pointing towards down, negative infinity, represents approaching in minus infinity in this case and plus infinity in that case. Now few graphs we could draw with transformation of this parent function 1 over x. For example, if I have graph of x plus 1, it really means that this graph has been translated 1 unit to left. So in that case we may have a graph which will be translated 1 unit to the left, kind of like this. You get the point, right? So like that we could draw some graphs. And if I have a function which is combination of quadratic and linear, we can have very different shaped graphs. To give you an idea, if I have a function which could be written in the factored form as x plus 2 times x plus 1 divided by x plus 1, in this case the restriction is that x is not equal to minus 1, since that will make the denominator 0. But you can cancel them. If you cancel them, you get x plus 2. However, you have to write the restriction that x is not equal to minus 1. In that case, graph of this function will represent the line x plus 2, but there will be a hole at x equals to minus 1, right? Since x equals to minus 1 is not in the domain of the function. So to give you a small sketch of this particular graph, it will be a line. So let me draw a light line first, which represents x plus 2. So x plus 2 is a line going through the y-intercept of 2, right? And slope of 1. At minus 1, the line will have a value of 2 minus 1, which is 1, right? But if you are sketching the graph of this particular function, in that case, there will be a hole at minus 1 and rest of the line will overlap. Do you understand? So that is kind of difference between x plus 2, a linear function, and the rational function x plus 2 times x plus 1 divided by x plus 1. And that's the meaning of the restriction x equals to x not equal to minus 1. So at minus 1, we will not have any corresponding value of the function. So this hole represents this vacant for minus 1, and minus 1 is not in the domain of the function. And if you have to write domain of this function, you'll say x belongs to real numbers where x is not equal to minus 1. Now in the following videos, we are going to have few examples to understand how to write restrictions on the rational functions, and then we will do some operations on rational functions like addition, subtraction, multiplication, division, and then we will explore the graphs. But from this video you got an overview of what are rational functions, what are not rational functions, how to write restrictions. To write restrictions you have to equate denominator to 0, and kind of how to sketch. So with that overview, I think we are good to go and begin with rational functions operations. Thank you and all the best.